Welcome back to The Explainer. Today, we're jumping right into episode 4.1, Switchgear Configuration and Technology Selection, specifically focusing on GIS versus vacuum breakers. Let's get to it. So, picture this. You're an engineer tasked with building a high-voltage substation in Singapore. It's an incredibly land-scarce, densely populated island, right? You literally do not have the luxury of sprawling open-air fields. Every single square meter comes with a staggering price tag. Singapore's land is just way too expensive for massive old-school switchyards, but electricity demands are absolutely skyrocketing. So what do? Well, engineers had to make a very deliberate tier-by-tier technology choice to drastically shrink these substation footprints right from the ground up. And that brings us to the first major solution: gas-insulated switchgear, or GIS. It's a highly compartmentalized, metal-clad dead tank design. By using GIS, you can safely pack massive, extreme voltage power switching capabilities into incredibly confined indoor spaces. It completely transforms the whole concept of a high-voltage substation. It literally turns what used to be a massive outdoor yard into just a sleek, compact building. It's a real game changer. Now, the underlying physics here are actually pretty fascinating when you compare GIS to the other major technology we use, vacuum circuit breakers, or VCB. Think of it like this. GIS is basically a pressurized diving suit. It survives those extreme hostile voltages by pumping in a specialized protective medium, specifically sulfur hexafluoride, or SF6 gas. On the totally opposite end of the spectrum, VCB operates like a vacuum-sealed container. Instead of adding a protective medium, it just removes the medium entirely. It uses a near-total vacuum to instantly kill the electrical arc. So you've got two totally different principles achieving the exact same goal: safely breaking an electrical circuit in a tiny footprint. So why do we deploy gas-insulated switchgear at the absolute highest voltage levels? Well, it all comes down to the exceptional dielectric strength of that SF6 gas. You see, at extreme transmission voltages, we're talking 400 or 230 kilovolts, an electrical arc desperately wants to jump massive distances through the air. SF6 gas stops that dead in its tracks. It dramatically shrinks transmission-level clearances compared to traditional air-insulated designs. To put that into perspective, if Singapore tried to use conventional air-insulated yards for these transmission stations, they'd need roughly 5 to 10 times more land area. So GIS isn't just a nice-to-have preference here, it's an absolute geographic necessity. But as we step down the grid, the technology shifts over to vacuum circuit breakers. By utilizing a vacuum bottle interrupter, which, remember, literally removes the medium altogether, you get near-instant arc quenching and incredibly low contact wear. And because these things don't rely on pressurized gas or oil, they boast extremely high mechanical endurance and a really low fire risk. This makes VCBs the absolute gold standard for indoor distribution networks. They're just perfectly suited for the much higher switching frequencies you typically see down in those distribution tiers, right near our commercial and residential buildings. Now, an absolutely crucial point to remember here is that neither of these technologies is universally better in some absolute sense. Real grid engineering is all about matching the exact right technology to the specific voltage tier and the specific environment. You can't just slap VCBs everywhere because vacuum interruption simply doesn't scale safely or efficiently to extreme transmission voltages. And on the flip side, you definitely can't put GIS everywhere because SF6 gas systems are expensive overkill for a standard local distribution substation. You really have to use the right tool for the right tier. And that brings us to the definitive voltage ladder mapping. If you're working on the grid, you really want to burn this into your memory. Here's the golden rule. At the massive transmission tiers at the very top, so 400, 230, and 66 kilovolts, the system relies strictly on gas-insulated switchgear. But the very second you drop down to the distribution tiers at the bottom, the 22 kilovolt and 6.6 kilovolt networks that branch out into neighborhoods and industrial parks, vacuum circuit breakers take over completely. This is the official assignment matrix for Singapore's electrical grid. No exceptions. All right, let's actually test that knowledge. Let's put you in the shoes of a substation designer for a second. You're looking at a blueprint for a brand new indoor 22 kilovolt substation facility being built in a super dense commercial district. You have to specify the primary breakers. Based on everything we've just covered, what exactly are you writing on that purchase order? Are you going with GIS or VCB? Think about it. Well, if you said VCB hit the nail on the head, you are exactly right. A 22 kilovolt substation is an indoor distribution voltage facility, which means it sits squarely within the vacuum circuit breaker tier. Specifying GIS in this scenario would mean severely overspending on totally unnecessary technology.
And obviously, trying to build an old-school air-insulated yard would just get your design rejected for wasting precious space. So 22 kilovolts means VCB, for sure.
Okay, before we wrap up, we really need to talk about the ghosts of the grid. Historically, a whole lot of switching relied on bulk oil volume-type circuit breakers. But let me be clear, the era of bulk oil is officially over. Because of the significantly higher fire risks and the heavy maintenance burdens compared to modern VCB or GIS alternatives, they have been completely phased out of Singapore's active standards. If you're on site today and you actually run into a bulk oil breaker, you are not looking at an active standard. You are looking at a relic that is slated for immediate replacement. So there we go. We've successfully unraveled the switchgear puzzle. Before this explainer, you already knew how to specify cable insulation by tier. Now, you can confidently assign GIS and VCB to their correct substations, meaning you can specify the exact right breaker technology for the job. But, having the right breaker is really only half the battle. Think about this for a second. Once you have these incredibly compact, highly efficient breakers, how do you actually wire them together into busbar configuration schemes so that taking just one breaker offline for routine maintenance doesn't instantly plunge an entire city district into a blackout? That delicate balancing act is a pretty fascinating engineering story, and it's exactly the puzzle we'll be solving next time. How do you keep the lights on when the breaker itself needs a break? Stick around, and I'll see you in the next explainer.